All right, in this video, we're going to cover some more information about linearly independent vectors in some vector space. And then we're going to do some examples related to this. But the last thing I want to do is some proof related to a set of linearly independent vectors. So let's let v1 through vk be independent vectors in some vector space V. Then if a1 v1 plus a2 v2 all the way up to a sub k v sub k is equal to some b1 v1 plus b2 v2 plus b sub k v sub k. If those two things are equivalent, then it turns out each of these pairs of coefficients are equivalent, i.e. exactly a1 is equal to b1, a2 is b2, all the way up to a sub k is b sub k. All right. Well, how do we prove something like that? Well, we can start with this statement up here. The a1v1 through akvk is equal to b1v1 plus through bkvk. Well, if we start with that statement, we can, since we're in a vector space, we can add the additive inverse to this right side. So that'll move this b1v1 over to the left, right? And that additive inverse should just be the negative of each of those coefficients. And then if we combine the v1s, well, all of that becomes a1 minus b1 times v1 plus a2 minus b2 times v2, and so on, is all equal to the zero vector, right? Because we added the additive inverse, so the right side should just become the zero vector there. Now, because v1 through v sub k are linearly independent, that means there's only one solution to this, and that is the solution, the trivial solution, that each of these coefficients is 0. So that's exactly what I've written here. a1 minus b1 is 0, a2 minus b2 is 0, and so on, which implies that a1 is exactly equal to b1, and a2 is exactly equal to b2. And all the way up through a sub k is equal to b sub k. So that actually finishes out our proof. And now, why might we see something, why is that interesting, right? Well, this isn't necessarily a true statement if our set of vectors are not linearly independent. And this quick example that I have right below here shows that. What if we have a vector x and a vector 3x? Each of these are vectors in some polynomial vector space, right, under the normal scalar multiplication and vector addition or polynomial addition. And they are clearly linearly dependent, right? 3x is 3 times x, so it is a scalar multiple of the other. In other words, it is a linear combination of x to get to 3x, right? So these are linearly dependent. But notice, if we take 1 times the vector x plus 1 times the vector 3x, well, that's 4x. That's not the only way we can write out 4x. We could have also written negative 2 times the vector x plus positive 2 times the vector 3x, right? We get 6x minus 2x is also 4x. So here in this case, we wrote out a linear combination of the two vectors, and here we wrote a different linear combination of the two vectors, and those were equal, right? a1 is not equal to b1, and a2 is not equal to b2. However, in the case, as this proof just showed, in the case that our vectors are a linearly independent set, then this is guaranteed that a1 is equal to b1 and so on. Okay. From there, I want to go over several examples related to linear independence. And as you've seen, I've already written out some of this here. We'll write out some new ones together here in a bit. But let's get started and look at this first question. Let's recall in R3 here, in R3 that the vector E1 is 1, 0, 0, E2 is 0, 1, 0, E3 is 0, 0, 1. We're going to determine if these three vectors are linearly independent, or if not, which means they are linearly dependent, let's find an explicit non-trivial linear relationship between them, which means let's write out one as a linear combination of the others. Okay? And I'd like to remind you of some stuff we've written down here on how we can solve something like that. So the first thing is, to remind you of, is a set of vectors are linearly independent if and only if this system here has a unique solution, and they're linearly dependent if that system has infinitely many solutions. And of course, we never have no solutions because the trivial solution, 0, is always a solution to this system. But we also noticed here that to be independent, that means exactly that we need the number of pivots in this system up here to equal the number of vectors, right? Which is the number of columns in our system. Okay, not including the augmented part. So that's what we're going to be looking for. And if we solve the system, that'll actually also show us what the relationship is if they turn out to be linearly dependent. And let's go through some examples now to see how that works. And first, we're starting with this statement up here, this first question, right? And pretty clearly, if we write this out and we write our vectors as our column vectors, pretty clearly this is immediately just the trivial solution with C1 equal to C2 equal to C3 equal to 0, right? Notice we have a pivot in every column, so we have 3 pivots, 3 columns, 3 vectors here. But also, quite literally, this says, because C1, C2, and C3 we think of as related to those columns, right, as the coefficients on those columns, we get exactly C1. 1C1 is equal to 0, 1C2 is equal to 0, 1C3 is equal to 0, right? So these 3 are certainly linearly independent. All right, so let's go on to a slightly more exciting question now. And that is, what if V1 is 1, negative 1, 2, V2 is 2, 1, negative 1, and V3 is 1, 5, negative 8? I've already written out the most of the solution for this. So what do? We start with, well, let's write our matrix with those vectors as our columns, and then let's row reduce until we either get it into reduced echelon form or just row echelon form. And if we have 3 pivots, then it's linearly independent and we're done. If it doesn't have 3 pivots, then let's go ahead and see if we can come up with our linear dependence, right? Let's come up with our linear combination of writing 2 of them, or 1 of them in terms of the other 2. All right, well, I've already done the row reduction here. So the first thing we can do is take R2 plus R1, and R2 now, row 2 is now 0, 3, 6. Then you can take R3 minus 2R1, and that'll cancel out the 2 there in column 1 of row 3. And the rest of the row is negative 5, negative 10. From there, if we divide this row by 3, we get 1, 2. And if we divide this row by negative 5, we also get a 1, 2. So those are going to cancel out. I did a few of those steps all at once there. But if you need to, you can always pause these videos and slow down and work the rest of that out yourself. But we see that we get this row-reduced matrix here. From there, we can actually solve for the a non-trivial vector that makes this linear combination equal to 0, right? So if we get a non-trivial vector, C1, C2, C3, that we multiply by this particular matrix to equal the 0 vector, then that tells us, that's our definition of linear dependence, right? A reminder of this statement up here again, right? If this system has infinitely many solutions, which means it has a non-trivial solution here, then we know that it is linearly, those vectors are linearly dependent, right? So here I have worked out, well, all right, if we call C3 our free variable, then notice that 1C2 plus 2C3 is equal to 0. So C2 plus 2C3 is 0. In other words, C2 is negative 2C3. Similarly, we can write out what C1, C2, and C3 are now. So C1 in terms of C3 is just 3C3, just by back solving this with everything equal to 0. And so if I just call C3 equal to T, then we get this solution vector here, and really infinitely many solution vectors here. So T times the vector 3, -2, 1. And in particular, if T is 1, that gives us exactly one solution vector there. And that is 3 times V1 minus 2 times V2 plus 1 times V3 is equal to the 0 vector. Let's see if that actually works, right? So we have our 3 vectors here. So 3 times V1, let's just look at the first row. 3 times 1 minus 2 times 2, so we have 3 minus 4 plus 1 is in fact 0. Okay, so it worked for the first row. Does it work for the second row? Well, 3 times -1 minus 2 times 1, so -3, minus 2 is -5, plus 1 times 5 is 0. All right, and then 3 times 2 is 6, minus 2 times -1 is +2, so we get 6 plus 2, minus 1 times 8, so in fact we get 0 there. So we did find a non-trivial solution, and we can use this to write V3 in terms of V1 and V2. In particular, if we just solve over the V3 and then multiply by -1, we get -3V1 plus 2V2 is equal to +V3. And we have finished our problem by writing one of those vectors in terms of the other two. It did not matter which one you wanted to solve for there or needed to solve for there. Just solving for V3 and writing that in terms of the other two was certainly faster, I think, just because we didn't have to divide by any coefficient. All right, and I'll pause this video here, and then we can start with another video to finish out the rest of these examples.